Assalamualaikum warahmatullahi wabarakatuh. I'm Zulfadli from Universiti Teknologi Malaysia, and today I'm going to talk about Lidar data acquisition, and this video is solely for the purpose of photogrammetry assignment. Okay, so what is Lidar? Lidar by abbreviation stands for laser detection and ranging. So Lidar data acquisition is not an easy task. We need to first determine the area of interest or AOI, and first, before we do a data acquisition, we need to set up a team. We need to line up a team that comprises of personnel that required to manage, document, process, and analyze all data associated with LiDAR system mapping, scanning, and digital image processing covering the entire project area. So first, we need to get a flying permit from Department of Civil Aviation. The LiDAR data collection will consist of a few components, which is ground control survey using GPS base stations, field verification, LiDAR sensor, initial measurement unit or IMU, digital camera, and an aircraft. So we need to first check accuracy of the system, and the system needs to be within the manufacturer's specification. So we can check this by doing system bench test. This is to ensure the system is in good working order before installation onto an aircraft. We can then proceed to do flight line designing. Usually it is based on client's budget and specification. Usually it is around 70% overlap and 30% side lap for urban area, and 60% overlap and 30% side lap for rural area. A test flight will need to be carried out before the actual data acquisition. Data analysis will be performed on the test flight data to ensure the system is in order before the aircraft and system is mobilized to the project area. The system is capable of detecting multiple discrete returns with a minimum of 4 or more potential returns for each outbound laser pulse in full waveform data, and records the intensity of each return. The airborne LiDAR system will be mounted on an aircraft, whether it is a helicopter, fixed wing aircraft, or UAV, or unmanned aerial vehicle like drone or something like that. So, but usually for area like Malaysia, Malaysia is a windy area, so helicopter will be a best option. And with helicopter, a GPS antenna can be fixed on the helicopter's tail, so there is no signal cut off due to distractions by any part of the helicopter. Alright, so for each data acquisition mission, a short session of static data collection will be carried out to initialize the GPS, IMU, and laser of the LiDAR system before takeoff. GPS times will be recorded on an adjusted GPS time at the highest precision to allow unique timestamp for each pulse. Urban area flying height should be lower compared to rural area because we want to capture more detailed area. The flying height is also based on flying below the lowest cloud height. This is to ensure the image is cloud and fog free. There should not be any cloud or fog between the helicopter and the ground. It's not necessarily a helicopter, of course. It can be a fixed wing aircraft and so on. So minimum point density should have an average of 2 points per meter square for rural and jungle area, and 10 points per meter square for urban area. This needs to be checked daily to ensure the requirement of minimum 2 points per meter square in each and every 1 kilometer square is met. If not met that day, that area will be reflown the next day, lower and slower. to increase point density and ensure final deliverables will meet terms of reference requirements. Calibration passes will be carried out before and after each mission throughout the project for data verification and monitoring the roll, pitch, and leading misalignment angles in Lidar point. Cloud. Lidar data will be properly registered and calibrated. During data acquisition, the aircraft will maintain constant flying height above ground to ensure that there are no data voids. The calibration site will need to have a following specification. 1. Perpendicular flight runs at different altitude. 2. The systematic bias correction will be calculated for roll, pitch, heading in mirror scale and shall be updated into the system calibration file. 3. The calibration flight will ensure the intensity returns are recorded properly to ensure the system calibration remains stable within the specification, and a calibration report should be published. So, surveyors should do around 50 to 100 checkpoints for each location for which Lidar data is to be verified. The checkpoints will be performed at calibration passes area or at selected in open flat terrain. Ground checkpoint surveys will be performed relative to project reference system using the same monuments used as GPS base stations for airborne GPS control. These ground checkpoints are used to ensure the quality and accuracy of Lidar data. Elevation data will be gathered as WGS 84 ellipsoidal heights, then will be adjusted to orthometric heights. The orthometric height will be heights by applying a correction to every data point, which will be identified by referencing to a local benchmark. All returns and collected points will be fully calibrated and adjusted to specified vertical data and classified as raw Lidar data in 1000 meter by 1000 meter tiling system. After all data acquisition is done, the surveyor should have deliverables such as boundary of the AOI, flight lines in KMZ and 3D polyline. 3 is the system installation and calibration reports. 4 is data acquisition operation and compliance report. 5 is the flight log, project manager report, data acquisition report, and daily mission summary. This report will have information on work progress, which includes aerial coverage percentage, equipment performance, and data quality and weather report. 6 is the roll point cloud. 7 is trajectory in ASCII format. 8 is raw digital imagery in GeoTIFF format. And 9 is the validation of vertical and horizontal accuracy report. So that's all from me today, and I hope this video can be informative for you. Thank you.